next property is one that we'll use quite often when we're dealing with rational expressions and we have our limiting value, our x is approaching a value that actually makes the denominator of our rational expression 0. Now before we get started on this one, I want to mention that whenever we're doing these properties and these basic definitions of limits, it's the way that we would deal with it if our limit exists and how you would find out what that limit would be. But sometimes limits don't exist. And there's actually 3 different situations that occur that would have it be where you could identify that the limit doesn't exist. So one of them is that you have unbounded behavior. So the function goes off to infinity or down to negative infinity as your x approaches a particular value. And if that's true, you have unbounded behavior and the limit doesn't exist. Another way that you might have a limit not existing is if it has oscillating behavior. So as you get closer and closer to it, the function just kind of bounces between values. It doesn't come in towards a specific value. And then the third type of a situation where a limit might not exist is if you have it that the left side limit does not match the value that the right side limit is as x approaches a value. Now those types of situations are discussed in a video that I've done called the intuitive idea of limits. And I've linked that video into the description of this one as well. If you want to review what to look for if a limit doesn't exist, you might want to check that one out. The reason I bring it up here is that when we are looking at these limits of rational functions as our x approaches a value, or the limit of ratio of 2 different functions that might not be polynomials, but they give me a 0 in the denominator, well, I really have to investigate more whether it's an unbounded behavior case or whether it's a case where I actually could get the limit. That it's an actual just punch out hole in the graph there, and as you approach a x value, the left side and the right side would have a limiting value that is approaching the same output, even though the function might not be defined right at that x value. And that's a key difference between a function evaluated at a point and the limit as x approaches that x value of the function. So when we're looking at a function evaluated at a point, we take out the x's, put in the number, and find out what the output is. But when we're looking at the limit as x approaches a value, we're looking at what the outputs approach as you get infinitely close to that value, but not necessarily what's happening right smack dab on it. The time that it will coincide to be the same value is if you have a continuous function there. And then we can use that idea to be able to evaluate our limits by actually finding out what it is there if the function's continuous there. And that's what a lot of the properties said that we've already done. But this theorem talks about what if you have functions that agree in all but one point in an open interval containing the value that your x is approaching. So let C be a real number and let f of x and g of x be equal for all the x's in an interval except smack dab on C in that open interval containing C. So as long as I can get on either side of the C and I can look at whether those functions agree in that interval, then if the limit as x approaches C of g of x exists, if it doesn't have the situation where it has unbounded behavior there or oscillating behavior there or a left side and a left hand and a right hand limit being different numbers, then the limit as x approaches C of f of x also exists, and those limit values will be the same as each other. Now there's some other properties and theorems that I want to do in this video, but before I do that, I do want to do some examples of this theorem, because this theorem is the one that we really will use quite often as we are faced with different limit questions where there's a fraction bar and a function in the numerator and a function in the denominator. All right, so for our first one, I have the limit as x approaches 3 of x squared minus x minus 6 over x squared minus 9. Now this is a rational function, and if my denominator function wouldn't be 0 in the denominator evaluated at the value that my x is approaching, then I would just use that rational function theorem that says that if that x value doesn't give you a 0 in the denominator, it's a continuous function there. So your limit will be the same thing as what you get if you plug the number through the rational function. But look what happens if I think about what the denominator would be if I did use 3 in for the x's. That would be 3 squared minus 9. Well, 9 minus 9 would give me a 0 in the denominator. And when I go through and see what happens in the numerator, 3 squared is 9, minus 3 is 6, minus 6 is 0. It gives me a 0 in the numerator as well. Now when I have a 0 in the denominator as well as in the numerator, and it's a polynomial divided by a polynomial, that's telling me that when I run a value through the x and I get a 0 out for the polynomial, x minus that number is a factor. And since that happened in both the top and the bottom, I have a common factor of x minus 3 that I can look at to remove as a common factor pair. So if I take and look at the limit as x approaches 3 of x minus 3 times x plus 2 over x minus 3 times x plus 3, just factor the numerator and factor the denominator, I see this common factor pair that I can remove. And this new function, this function of x plus 2 over x plus 3, matches my original function everywhere except at 3. That means that as the limit as x approaches 3, I'm getting infinitely close to 3, not right on 3, I can evaluate this limit and get the exact same limit that I would have for my original function. So I can come in it that way. So now, as I think about what happens if I put 3 in for the x's in the new function, limit as x approaches 3 of x plus 2 over x plus 3. Well, 3 plus 3 gives me a 6 in the denominator, not a 0 anymore. And in the numerator, 3 plus 2 gives me a 5. So I get that this original limit will also be 5/6 by that theorem about the limit of functions that agree in all but one point. Okay, let's see how we can apply it here and just get some more practice. So limit as x approaches -1. I have a function divided by a function. I check and see what happens when I put the value that the x is approaching into the denominator. Well, -1 plus 1 is 0. And in the numerator, -1 quantity squared is 1, plus 3 times -1, well, that would be 1 subtract 3 is -2, plus 2 gives me a 0 in the numerator as well. And again, since it was a polynomial divided by a polynomial, that's telling me that x minus that -1 is a common factor. So I have the limit as x approaches -1 of, in the numerator it factors as x plus 1, x plus 2. In the denominator I have x plus 1. I can remove that common factor pair to get the new function that agrees with the original all but at -1. And this limit does exist, and its limit is 1. So -1 plus 2 is 1. And that also will be the limit of my original function. So when might it not exist? If you have a value of x that when you run it through the denominator you get a 0, but when you run it through the numerator you don't get a 0, that will be one of the cases there you have that unbounded behavior, and so that would be a situation where it doesn't exist. Now, just because I get a 0 over 0 doesn't guarantee my limit is going to exist. I have to evaluate and see what happens. So here's 2 more examples. So I have my limit as x approaches 5 of this rational function, a polynomial over a polynomial. And the first thing I want to do to try to evaluate this limit is see what happens when I run the value that x is approaching through the denominator. So 5 squared is 25, minus 10 times 5 is minus a 50, so 25 subtract 50 is negative 25, plus 25 gives me a 0 in the denominator. Now what happens when you run the 5 through the numerator? Well, that's going to be 25 minus 30, so that's a negative 5 plus 5 gives me a 0 in the numerator. And that tells me that x minus 5 is a factor of both the numerator and the denominator. So I write this as the limit as x approaches 5 of x minus 5 times x minus 1. And in the denominator, x minus 5 times x minus 5. Now I see that I have my common factor pair of x minus 5 in the numerator and the denominator that I can remove. And then when I think about running the 5 through the x's in the denominator to do the process again, well, 5 minus 5 gives me a 0 in the denominator again. But 5 minus 1 is a 4 in the numerator. And when I have a 0 in the denominator but a non-zero number in the numerator, that's where we would have a vertical asymptote of our rational function, not a hole in the graph. And if it's a vertical asymptote, it's got that unbounded behavior. So this limit does not exist. How about the next one? Well, as x approaches 7, 7 minus 7 is a 0 in the denominator. In the numerator, I have 7 squared is 49, plus 2 times 7 is 14, so that's 63, and then 63 minus 4 is not a 0. So you get your 63 minus 4 is your 59, not a 0. So not 0 divided by 0, the graph itself would have a vertical asymptote at x equals 7, unbounded behavior. So it does not exist. Just to put another one up here so we remember, if I have the limit as x approaches, say, 4, of x minus 4 over x plus 3, then as x approaches 4, I look at what happens in the denominator first. Well, 4 plus 3 is 7. It doesn't give me a 0 in the denominator. And that was back to that theorem in the earlier video of the rational function. If it doesn't give you a 0 in the denominator, then you can go ahead and evaluate the limit by seeing what's happening right at that point to what the limiting value would also be. So I will have a 7 in the denominator, and in the numerator I have 4 subtract 4 is 0. But it's okay to have a 0 in the numerator. In fact, when you have that, 0 divided by 7 is 0. So that limit value would be 0. And if I had another limit where I didn't have a 0 in the denominator, as well as I don't have a 0 in the numerator, then it would just be whatever that value came out to represent. So that gives you some examples of what we would do if we had a common factor. Let's see a couple other things that might occur. So here I have a limit as x approaches a value of a fraction, but they're not a polynomial divided by a polynomial. So it's going to be situations where there might be other techniques I need to do to figure out what's happening if I do get a 0 over 0 case. So when I look at what the x is approaching and I evaluate what's going on in the denominator, as x approaches 0, the denominator would be 0. Then what's happening in the numerator? Well, 0 plus 1 is 1, and the square root of 1 is 1, and 1 minus 1 gives me a 0 also in the numerator. So I know there should be some sort of simplification technique I can do to see what this common factor is that might remove. But with the radicals and the two different terms, the technique I'm going to do here is to rationalize the part of the ratio that has that radical in it. Now remember, to rationalize when I had two terms with a square root, we want to build top and bottom by the conjugate. So I have my square root of x plus 1 minus 1 over my x, and I want to build top and bottom by the conjugate of the square root of x plus 1 minus 1. And the conjugate of it is the square root of x plus 1 plus 1. So you keep your terms and just change the sign in between for the conjugate. Now let's multiply it out. That's the limit as x approaches 0 of, well, square root of x plus 1 times the square root of x plus 1 is x plus 1. Then the outers, that will give me plus the square root of x plus 1. And then with our multiplication of negative 1 times the square root of x plus 1 for the inside terms, that's minus the square root of x plus 1. And then a negative 1 times a positive 1 is a minus 1. And then this is all over, and keep the denominator factored, or when you're doing a problem, whichever one has the part that's not being rationalized. Keep that factored. Okay, now combining like terms in the numerator, I have a plus square root of x plus 1 and a minus square root of x plus 1, and they remove. And that's why we did the conjugate. And then I have x plus 1 minus 1, so the plus 1 and the minus 1s combine as like terms, and I just have that factor of x in the numerator. And I left the denominator factored so I could see that common factor when it occurs, and now I have a common factor pair in the numerator and the denominator when we remove that common factor pair of x. And now look at what happens when you plug in the 0 for the x. 0 plus 1 is 1. The square root of 1 is 1, and 1 plus 1 is 2. So I get a 2 in the denominator, not a 0 anymore. So this new function that agrees with that everywhere in an open interval around 0 except at 0 actually does have a limit in the numerator of a 1. In the denominator of 2, my limit comes out to be 1/2. And so the limit of my original function is the same as the limit of that other one that agrees with it everywhere except at 0. So 1/2 is my limit. So there we needed to use the multiply top and bottom by the conjugate. How about this next one? Well, this is the first time we've seen delta x as my limiting value in variable instead of x. Remember, delta x is a two-symbol representation for one idea of the change in x. So I want to think of this as one entity and look at where it is in my limiting process, and that's what is your variable that's approaching. So delta x approaches 0. So if I put a 0 in for the delta x, I get a 0 in the denominator. If I put a 0 in the delta x in the numerator, I have 5 over x minus 5 over x, so that's also a 0 in the numerator. And I'm like, what do I do with this? Well, this is a complex fraction. It's a fraction over a fraction. So one way you could handle this is to get common denominator and combine your fractions in the numerator. And then once you do that in the numerator of it, we'll take care of the overall fraction. So this is the limit as delta x approaches 0 of my lowest common denominator in the numerator is x plus delta x times x. So I'm going to build my first fraction by x. And the second fraction I'm building by x plus delta x. And don't forget that that's all over delta x, and I can think of that as a delta x over 1. Okay, so now in the numerator you have a common denominator. So you're going to combine the numerators and keep that common denominator and then have your fraction bar with that other fraction. So that's a limit as delta x approaches 0 of, so I have 5x, and take that minus with the 5. So minus 5x minus 5 delta x. And that is over x times x plus delta x, and that is over delta x over 1. Now combining like terms in the numerator, 5x minus 5x, the 5x like terms combine and remove. So I just have a negative 5 delta x over my x times x plus delta x. And then I'm dividing it by this delta x over 1, so I'm going to take care of that division by multiplying by the reciprocal. So this is times 1 over delta x. Now if I write this as, remember multiplication is straight across the top, straight across the bottom, that's the limit as delta x approaches 0 of negative 5 delta x divided by x times x plus delta x times delta x. And now I can see that common factor of delta x that removes. And then as I look, as delta x approaches 0, the delta x is approaching 0. So I think of it with 0 where the delta x is, and I get negative 5 over, and in the denominator it's x times x, or x squared. So negative 5 over x squared. So for this one, we actually got an expression for our limit instead of a specific numerical value for our limit. All right, so there's a couple more theorems that I want to put on the board, and then we'll finish up with at least this segment of my videos on properties of limits. The last two that we're going to do in this video are special limits that involve trig functions. So here, if I look at what's happening as x approaches 0, I'll have a 0 in the denominator. And then as x approaches 0, the sign of something approaches 0 also approaches 0. So I do have a 0 over 0 case, which when you have a 0 over 0 case, it's called an indeterminate form. Well, this takes a little bit more work to actually do simplifications that would show you what its value is. So it's one where they're saying, you know, it's better just to recognize that limit, and we're telling you that it limits, the limit value is 1, so that when you see that in future situations, you'll know that limit. Also, the limit as x approaches 0 of 1 minus cosine x over x. It's another one that will give us a 0 in the denominator and also a 0 in the numerator. So when you identify the limit as x approaches 0 of 1 minus cosine x divided by x, know that that limit is 0. And here are some examples. So in this one, I have the limit as x approaches 0 of sine of 3x over x. So it's very similar to this one, but not quite it. What has to happen is when you're looking at the limit as x approaches 0, your sign of the argument and what is in this argument and the denominator have to match for that limit to be a form of the one that we are utilizing here. So in this case, my denominator really needs to be a 3x. The limit as x approaches 0 of sine 3x over 3x. Now, I cannot pull that numerical coefficients of angles out in front of the trig function. That is not an equivalent process. But what I can do, since the denominator doesn't have an action on the variable, I can actually multiply that denominator by 3. And if I do that, I have to be fair and multiply the numerator by 3 as well. Now the denominator 3x and the sign of 3x, that is the part that is similar to our original definition here. This 3 that's multiplied in front of the sign x that I had to do to make it an equivalent statement, that is just a factor in front of the sign of 3x. So I can actually pull that out of the limiting process from a property we had in the video that I've linked in the description. So in front, then I have sine 3x over 3x. And the limit of that as x approaches 0. So this is an equivalent form of our limiting process being 1. So then that's 3 times 1, which is 3. Next up is our limit as x approaches 0 of 1 minus cosine x over 5 times x. This is a little different because the coefficient of 5 is actually just multiplied to the x in the denominator. It's not a factor in the angle that a process of a trig function is acting on. So this factor of 5 in the denominator, I can use my property that the limit as x approaches c of a constant factor times a function is equal to the constant times the limit of the function. So because that 5 is in the denominator, it's actually a 1/5 that is the constant factor in front of this function. And so it's 1/5 times the limit as x approaches 0 of 1 minus cosine x over x. By definition, that limit is 0, so it's 1/5 times 0, or 0. So this gives you a little bit more foundation on limits and properties of limits. There will be other videos that I do, and as I get more completed and uploaded, I will link those also into this description, so you have a full library of things that you can look up if you're looking for specific help in a particular limiting process.